165 launches in a single year. That is what SpaceX did in 2025. China managed about 70. The Space Launch System managed 0. The gap is not closing, it is widening. But launch counts only tell half the story. The real shock sits behind the rockets. You already watch these scoreboards, you already track the gap. Rockets do not build themselves. Satellites do not assemble overnight. Workforce size shapes the whole game. China fields up to 200,000 people in its space program. SpaceX runs with about 13,000 total workers. NASA's rocket ecosystem sits near 8,000. That spread changes how each system moves, and it explains why the race feels uneven from the outside. Because here is the core constraint. The Space Launch System is built for heavy deep space missions. It is not built for rapid launches. Artemis Y proved the rocket could fly, but it also exposed how massive the workforce had become. Estimates show the effort likely involved over 14,000 workers at its peak. By 2026, that number dropped closer to 8,000. That includes government staff and major contractors. Think about that for a second. Thousands of people supporting one heavy rocket system. That scale shapes everything that follows. Now look at the productivity math. Using a rough estimate of 8,000 full-time workers over more than 10 years makes the ratio striking. Artemis Y represents one launch across that span. That works out to roughly 8,000 employee years per flight. SpaceX, with about 13,000 employees, produces roughly one launch per 79 workers each year. You have seen numbers like this in other industries. Output per worker always tells a story. High-volume systems reward repeatable design. Low-volume systems focus on one massive push. Rockets follow the same logic. SpaceX built the Falcon 9 rocket around reuse. The first stage booster lands and flies again. That single choice changed the entire production rhythm. Instead of building a brand new rocket each time, they fix it and fly it again. That cuts build time. It spreads fixed costs across many flights. It also raises launches per worker fast. The Space Launch System took a different path. Each core stage is used once. Each launch is a major campaign. That design trades flight rate for raw lifting power. The heavy rocket can send about 95 tons toward the moon. That is 95 tons, heavy as 15 pickup trucks. Falcon 9 typically carries around 25 tons to low Earth orbit. Different tools serve different goals. Here is the thing. Launch cadence compounds like interest in a bank account. Fly once a year and your learning curve moves slowly. Fly every few days and the feedback loop tightens. SpaceX ran 123 Starlink missions alone in 2025. Each one fed data back into operations. Each one improved the system, but the metric still has limits. Comparing pure flight counts misses a key detail. The heavy government rocket carries deep space cargo. It supports crewed lunar missions. Falcon 9 focuses mostly on commercial and satellite work. Still, throughput tells you something real. High cadence reduces cost per launch. Airlines learned this decades ago. The more often a plane flies, the better the maintenance data becomes. Rockets now follow that same pattern. Meanwhile, the heavy rocket followed an older approach. Teams reused hardware from the space shuttle era. The RS-25 engines came from the shuttle program. Those engines are extremely powerful. They are also expensive and complex. Each one needs detailed inspection and preparation. Solid boosters arrive in large pieces from Northrop Grumman. Teams must stack and connect each piece precisely. Nobody talks about this part. Integration labor grows quickly with systems this large. Because each rocket stage is new, the workforce must repeat full assembly cycles every time. The core stage alone stands about 98 meters tall. That is 98 meters, roughly a 32-story building. Building hardware at that scale takes time and skilled labor. That is unavoidable physics. Boeing handles the core stage work. Reports noted roughly 400 layoffs connected to program delays. Later updates suggested the reduction was closer to 200 positions. Most of those workers sit at assembly facilities in Louisiana and Alabama. The work spreads across multiple states. That structure supports political stability and regional jobs. It also creates coordination overhead that private launch firms often avoid. Then comes the upgraded version that adds the exploration upper stage. The upper stage is the top rocket segment that pushes the spacecraft farther. Building that new stage introduces fresh work streams. This is where it gets interesting. Large distributed programs often trade speed for stability. The heavy rocket uses proven engines and solid boosters. That reduces unknown risks. It also locks in older building methods that require many hands. There was a near-miss moment many overlook. During preparations for the first flight, teams worked through hydrogen leak checks repeatedly. Hydrogen is extremely small. It slips through tiny gaps. Ground teams spent weeks chasing those leaks. One scrub came less than 40 minutes before launch. Fixing those leaks required careful sealing changes. Teams ran repeated tanking tests. Each test moved the program forward step by step. That slow grind is part of why large government rockets demand big workforces. Another close call happened during early core stage testing. In 2021, the first hot fire test shut down early at about 67 seconds. Engineers needed a full retest months later. They traced the issue to conservative engine limits and updated the software. The second test ran the full 8 minutes. That success cleared a major technical hurdle. It reflects mission priorities set years earlier. The system favors certainty over speed. Safety drives the schedule. That approach protects crews. It also slows iteration. SpaceX chose a different rhythm. They test fast, adjust fast, and fly again. Their flat structure shortens decision loops. Look at the production model first. They use vertical integration. That means they build most parts in-house. Engines, tanks, software. The Raptor engine and the Starship heat shield all come from tightly linked teams. Fewer outside handoffs mean fewer delays. The government model spreads work across multiple firms. Boeing handles major rocket pieces. Northrop Grumman builds solid boosters. Lockheed Martin works on the Orion spacecraft. Each handoff adds review steps. Each review adds time. Safety improves. Speed often slows. You see where this is going. But the vehicle design matters just as much. Reusability and production flow must support the pace. Early in the Falcon program, SpaceX faced near failure. 3 early rockets failed between 2006 and 2008. One engineer later said they were about 30 seconds from shutting down the program financially. Because of those early failures, they doubled down on vertical integration. Merlin engines, tanks, and software moved under tighter control. The goal was simple: reduce delays, cut supplier risk, speed iteration cycles. That decision shaped hiring for the next decade. By 2015, boosters started landing routinely. Reuse became practical. The breakthrough came when engineers perfected the landing sequence. Here is how they actually did it. They added grid fins near the top for steering. These are metal wings that guide the booster back through the atmosphere. They deployed landing legs seconds before touchdown. They mastered the engine restart sequence to slow the rocket down exactly when needed. They landed on autonomous ships in the ocean using advanced software. Each step required tight coordination between hardware and software. When one early booster tipped and exploded on a drone ship, they traced the issue to hydraulic fluid limits. They redesigned the steering system and flew again months later. That fast loop solved the reusability problem. It turned recovery from a risky experiment into normal operations. The Block 5 version was designed for fast turnaround from the start. Today, some boosters have flown more than 15 times. Turnaround time dropped from months to weeks. Because the real story is not just how rockets are built. The real story is what pay systems push teams to do every single day. Average total pay at SpaceX sits near $199,000 a year. Government contractors often sit closer to $120,000 to $150,000. Same industry, same talent pool, very different systems. Higher pay often signals a company fighting for top talent. Base salary alone often runs high, but the stock piece is key. It ties personal gain directly to company speed and success. If the company grows fast, shares gain value. That turns every design win into a personal reward. That connection pushes faster iteration cycles. Contractor engineers usually receive fixed salary bands. Raises follow structured reviews. Equity upside is usually limited. The structure rewards consistency more than aggressive risk-taking. That difference shows up in hiring patterns. SpaceX attracts people comfortable with pressure, long hours, rapid changes. Contractor roles often attract engineers who value stability. The motivation levers simply pull in different directions, and then the pressure keeps rising. The real workforce stress test arrived with Starship. Starship is the fully reusable heavy rocket now under development. It uses Raptor engines that burn methane fuel. Methane burns cleaner than older fuels. Cleaner burn helps engines survive multiple flights without deep cleaning. Each booster uses about 33 Raptor engines. Each ship uses 6 more. Building that many engines requires massive manpower. That explains the steady rise toward 15,000 employees. Welders, technicians, and test crews expanded month by month, and then the launch cadence started to rise again. During one pressure test, a tank showed unexpected stress cracks. The failure happened within seconds of full load. Teams redesigned the steel thickness and weld pattern. The next tank passed. That rapid loop reflects the broader culture. They build the tank, then the engine section, then stack both pieces, and then the rocket flies. The goal is aircraft-like reuse. That shift demands massive test cycles. It also demands constant hiring to support the pace. Now look across the ocean. China built its program around scale first. More than 1,000 partner groups feed parts and testing. Because of that structure, China can field huge teams on single projects. Total space-related staff sits between 100,000 and 200,000. Even the low estimate dwarfs most Western launch teams. In 2025, China completed about 70 orbital launches. Divide that by the workforce. You get roughly 1 launch per 1,400 to 2,800 workers each year. That is the efficiency baseline. Resource efficiency favors the smaller team. But here's the thing. China's not trying to match Falcon 9 Cadence yet. Its Long March 5 heavy rocket focuses on big missions. Space station modules, deep space payloads. These missions take longer to prepare. They also demand larger support networks. That steady approach comes from human decisions made decades ago. After early failures in the 1990s, Chinese planners prioritized reliability. Each rocket family went through extended ground testing. The goal was fewer surprises on launch day. That mindset still shapes the workforce today. The system values consistency over burst speed. During early Long March 5 development, one engine failure delayed the program nearly 2 years. Engineers traced the problem to the engine fuel pump. It failed under high stress. Fixing it required major redesign work. China expanded test teams. Reliability improved afterward, but the size creates its own friction. Large state programs move methodically. More layers mean more reviews. More reviews mean slower iteration. 2 different playbooks competing in real time. And the efficiency math keeps showing up. Reusable rockets change the whole equation. China is moving to close that gap. The Long March 8R reusable rocket entered testing. Engineers aim to recover the first stage vertically. That shift could reshape the workforce math over time. Several Chinese commercial firms are now testing reusable boosters too. Companies like Landspace and Galactic Energy run leaner teams than the state giants. Early vertical landing tests already reached low-altitude hops. Success here could compress the national average. Stay with me here. The hard part is not landing the booster. The hard part is doing it cheaply and repeatedly. NASA flew the space shuttle for 30 years. Each ship required months of repair work. Costs stayed high. Turnaround stayed slow. That lesson echoes inside planning rooms today. Internal studies highlight reuse as the next major goal. Some documents target partial reuse by the late 2020s. But China's space program serves multiple missions at once. Military launches, weather satellites, human spaceflight. 3 rocket families handle these jobs. That diversity spreads the workforce across many tasks. SpaceX focuses heavily on Falcon and Starlink. Narrow focus often boosts efficiency. Wide scope often builds resilience. Both models have strengths. Let that sink in. Financial math adds another layer. One heavy government launch costs over $4 billion today. That is $4 billion, enough to build roughly 8,000 homes. Multiply that by 134 flights. The yearly total would approach $500 billion. That number dwarfs the entire annual space budget. Even aggressive cost cuts would leave a massive gap. The economics simply do not scale cleanly. A single launch is often estimated in the multi-billion-dollar range. Falcon 9 launches cost far less per flight. Direct cost comparisons have limits because missions differ. Still, per-launch economics influence how often vehicles fly. That feedback loop shapes the workforce ratio. Reusable rockets reduce the number of new parts needed each mission. Fewer new parts mean fewer factory hours. Fewer factory hours mean smaller standing teams. Each time a booster lands intact, the same workforce supports another mission without building from scratch. Over dozens of launches, labor per flight keeps falling. The system rewards repetition. It punishes low cadence. Expendable heavy lift stretches labor costs. Total program costs reached about $23.8 billion through the first flight timeframe. Analysts estimate labor made up roughly 20 to 40% of that total over the years. Because each rocket stage is new, the workforce must repeat full assembly cycles every time. Once that architecture locks in, changing course becomes extremely hard. Nobody talks about this part. Starlink quietly drives huge staffing demand too. Thousands of satellites now orbit Earth in the Starlink network. Each satellite needs manufacturing, testing, and ground support. Teams help deploy the network globally. The result shows up in system coverage. That global footprint demands constant monitoring. Ground stations must track satellites every minute. Software teams manage updates. Operations crews handle network uptime. All of that work sits inside the same workforce umbrella. SpaceX does not isolate Starlink into a sealed division. The network program spreads across existing teams. Antenna designers work alongside rocket engineers. That cross-pollination speeds problem solving. Engineers shift between Falcon upgrades and Starship work when needed. That flexibility showed up clearly over the last 5 years. Falcon 9 kept flying at record pace. At the same time, Starship prototypes rolled out one after another. Same workforce base, 2 major programs advancing together. This matters more than it sounds. Competitors feel the pressure. Amazon plans thousands of satellites of its own. China also pushes forward with its own network plans. Yet workforce scale still favors SpaceX today. Launch frequency and satellite output reflect that edge. Looking ahead, the real race centers on reusable heavy lift. If vehicles like Starship mature, deep space missions could fly far more often. Fuel depots and lunar logistics would expand. The industry would shift again. That shift is already underway. China's planners appear to follow a similar path. Their Long March 9 concept targets heavy lunar missions. At the same time, they invest in reusable boosters for frequent flights. 2 tracks, 2 tempos. NASA understands the Cadence ceiling. Recent planning focuses on reducing the gap between flights. That would be a meaningful improvement. Yet even that best case remains far below triple-digit launches. Physics and production limits still apply. The heavy rocket is expendable. The pieces are custom. Management can improve efficiency. It cannot erase structural limits. Still, the technical achievement remains significant. Artemis I proved the rocket works. Lockheed Martin leads the Orion spacecraft work. Orion is the crew capsule that carries astronauts around the moon. The capsule survived temperatures near 2,800 degrees Celsius during re-entry. Its life support and heat shield systems are designed for deep space return speeds. Those systems performed perfectly. Capability and cadence do not always rise together. The market now shows both models operating side by side. SpaceX flew about 165 missions in 2025, while China managed roughly 70 and NASA's heavy system flew 0. The Falcon 9 rocket has landed hundreds of times and no other rocket has landed once and flown again. This massive gap in launch rates is widening every single month. By the time competing heavy rockets finally fly, Starship will already have years of flight experience. That is not just a plan, that is the current schedule.